Hello, I'm Abhipsha, PhD student at Indian Institute of Science, and I'm delighted to present our work RMLVQA, a margin loss approach for visual question answering with language biases. This is a joint work with Shravanti Addepalli and Professor Venkatesh Babu at Indian Institute of Science. First, we present an overview of our work. Visual question answering is the task of answering a natural language question based on an image. While considerable research has been done, VQA models still suffer from the language bias problem, where models learn a spurious correlation between the question type and the answer while ignoring the image. To solve this problem, we learn a robust margin loss where the margins are not only estimated from the training data but also learned from the model itself. For the latter part, we introduce a bias injecting component trained by the cross entropy loss. We secure state-of-the-art performance on the out-of-distribution VQA-CP dataset and competitive performance on the in-distribution VQA-V2, which makes our model the most robust out of the competitive methods. Now we present details on the proposed approach RMLVQA. In visual question answering, given this question, the model has to understand the image fully and focus on the correct region to answer it. Now suppose the training set is such that most of the times the answer to this question is man, few times it's woman, and very less number of times it's the children. The model therefore sees that only men are wearing glasses mostly in the training set. Therefore on the test set, even after seeing this woman wearing the glasses, the model still predicts man, as it has memorized that glasses are mostly worn by men in the training set. It starts ignoring the image completely. So this pink color phrase at the beginning of the question is called the question type. Models tend to learn a spurious correlation between this question type and the answer. These are some other question type examples from the datasets. Now ignoring the image in this way is not desirable, right? But how do we even evaluate what our model is exactly learning? To do that, people came up with this dataset called VQA-CP. You can see that its train split has a lot of imbalance in each question type. So now for the test split, for the same question type, we let the imbalance stay, just that we change the frequencies of each answers. For example, you can see the question type how many and check the differences in answer distributions. This test split helps us evaluate what the model actually learned. Here we see that just by changing this answer distribution, the accuracies go down drastically, showing how rampantly the language biases are present in standard models. To solve this problem, some works used augmentation-based methods to balance out the skewness in the training data, but this requires cumbersome methods for generating the augmentations. Another line of work uses an auxiliary question-only model, which simply takes the question as the input and predicts if the given training sample is biased or not. If yes, then the model kind of unlearns it. If no, then the model puts more focus in learning it. Visual grounding-based methods ensure that the models are able to achieve visual grounding, but they require human annotations as supervision. The margin loss-based methods tend to overfit to the out-of-distribution test set that we showed, but perform very badly on in-distribution data. To begin with, we first show the angular margin loss introduced by ArcFace, the face recognition method. To do that, we obtain the commonly used cosine normalized form of cross entropy loss. We refer everybody to the ArcFace paper for more details on how to do this. This is the margin loss where a constant margin penalty is placed inside the cosine. So given a binary classifier, while the normal cross entropy loss allows no margin between the two classes, the ArcFace formulation separates the two by a distance m. As our dataset has a lot of class imbalances, a fixed m won't do. What we do is, for a given question type like what color, we first calculate the answer frequencies in the training set, and using these find the probability of each answer. Then we invert it by subtracting these probabilities from 1. So now the rarest color has the highest margin and vice versa. This is because the rare answers need to have a higher margin from the decision boundary than the frequent ones. We call these the frequency based margins. However, the problem with this formulation is that now the model will focus too much on the sparse answers like black and tend to overfit to them. To do away with this overfitting, we randomize the margins by passing them through a Gaussian. This stochasticity increases robustness, as now for each training instance having the same answer, the margin values vary. The resultant loss with the adaptive margin loss looks like this. The obtained margins are approximated from the training data as an average. They can be used to train the model as shown here. We feel that it still lacks some per sample information. To add this per sample information, we add a new classifier CB. As shown here, which generates the logits FB and is trained by the cross entropy loss. This section, that is the blue box known as the bias injecting component, learns the bias in the model. We use the predictions of this classifier head to generate the per instance margin values. So we utilize the prediction probabilities of the bias injecting component and invert them to obtain the instance-based margins. Finally, for each training sample, we combine the randomized frequency-based margins with these per sample margins. The bias injecting component learns the bias in the dataset and hence clusters the feature space with respect to the question types. We use the SoupCon loss with respect to the ground truth answers. This helps keep each answer within a question type cluster distinct in the feature space. Our total loss is the sum of the margin loss, which uses the combined margins, the cross entropy loss to train the bias injecting component, and the SoupCon loss. To make the predictions independent of the test set distribution, we do test time ensembling. The margin loss trained Logit is an expert on the out of distribution data, but the bias injecting component is an expert on the in distribution data. So we combine them. So finally, we combine the predictions from the two classifiers and generate the final predictions, which uses a weight alpha for the combination. So the value of this weight alpha is set to be 0.5. Comparing with competing methods, we find that our method achieves state-of-the-art on the out-of-distribution VQA CP while maintaining competitive results on the in-distribution VQA V2 validation set. More significantly, out of all the competitive methods, our method is the most robust to both the datasets as evident from the value in the difference column. This TSNE plot shows the feature space when trained by A, the vanilla margin loss, B, the randomized margin loss, and C, the randomized margin loss plus bias injecting component. The colors indicate the different question types. We see that with the addition of the bias injecting component, the feature space is much better clustered with respect to each question type, verifying our claim that this component clusters the feature space on the question type automatically. In this qualitative example, which reads what color shirt is the man with the ball wearing, the ground truth answer is red, right, because this person is holding the ball, but the baseline focuses on the wrong person and hence answers blue. Our method is able to focus on the correct region to output the correct answer red. So we have reached the conclusion where we say that in summary, we introduce an adaptive margin loss based method to solve the problem of language biases in VQA. We achieve state-of-the-art performance on the out-of-distribution VQA CP dataset, and we do test time ensembling of the two classifier heads, which makes our model robust to any answer distribution. But there are some drawbacks as well. For example, our model still utilizes the knowledge of the bias to calculate frequency-based margins. What if the knowledge of the exact bias is not known? Then what do we do? And how do we ensure better visual grounding? These are some of the future works that we plan to address in future. Thank you.